Welcome, cosmic comrades. If you came to learn about where babies come from, I have some news for you. I have no idea either. But if you came to learn where baby stars came from, I'm your guy. Stars, like many organisms on Earth, come from generations of previous stars, and they have life cycles that feed into the next generation. Stars form usually from massive clouds of gas in space that come from dead stars of previous generations. And these massive clouds of gas begin to collapse due to the immense amount of gravity. Usually, when stars form, they are made mainly of hydrogen. Assuming they are massive enough to fuse hydrogen, which we are indeed assuming, they will start to fuse hydrogen in their core into helium using nuclear fusion. Welcome to the main sequence. Also, like most earthly organisms, stars breathe, expanding and contracting as they evolve. As the hydrogen in the core runs out, the core becomes unstable and contracts some. This increases the pressure and the temperature of the star, allowing more fusion of hydrogen in the shell around the core. The outer layers of the star expand from the increased internal heat. The expansion makes the outer layers cooler and redder, sending the star through the subgiant branch into the red giant branch. As the star enters the red giant branch, the temperature in the core increases again, reaching some 10 million Kelvin, at which point fusion of hydrogen in the core into carbon can occur. At these hot temperatures, the gas is no longer an ideal gas. It's a degenerate gas, which just means that the pressure of the gas does not depend on the temperature, allowing the conversion of helium into carbon to happen very quickly in a process known as the Helium Flash. After that, the star steadily fuses helium in its core, with the hydrogen burning shell around the helium burning region. The star is now a helium burning star. Now the star is in the horizontal branch, where it will continue fusing helium into heavier elements, carbon and sometimes oxygen. The outer layers continue to expand and cool, stopping fusion of the hydrogen in the outer layers while the core becomes inert with the non-burning helium and hydrogen shells. The core contracts some. Just when you thought that star was done with that hydrogen, boom, it fuses not only more of that hydrogen, the star starts to fuse both the hydrogen and helium shells of the star, sending it into its asymptotic phase. Now, the outer layers of the star keep expanding to a point where the outer layers of the star are too far from the gravitational center, making them too weakly bound by the gravity of the star. And the outer layers now start to depart from the star into the interstellar medium. This ejected gas is known as a planetary nebula. The planetary nebula immediately has exactly nothing to do with planets. This term came from the nebula looking vaguely like a planet through a small telescope, small and fuzzy and stuff. Like many other terms in astronomy, these words are misleading, but they stuck around because tradition? I don't know. While planetary nebulae can be beautiful, we're not done yet. Planetary nebulae leave behind the core of the star called a white dwarf, made mainly of carbon and oxygen that was fused from the helium previously. It'll stay stable as the remnant core, granted it is under the mass of the Chandrasekhar limit, 1.44 solar masses, determined by this dude, Subramanian Chandrasekhar. A white dwarf is extremely dense, around 10,000 to 1 million grams per cubic centimeter. They generally are around the mass of the Sun and only slightly larger than the volume of Earth. To put this into perspective how dense this is, 1 teaspoon of a white dwarf is the same weight as an elephant on Earth, 5.5 tons. All this mass is supported by electron degeneracy pressure that happens because of the Pauli exclusion principle developed by Wolfgang Pauli, which is not some elitist rule from a secret society that bans anyone named Pauli. Instead, it's just some quantum physics stuff, which we will learn finds its way into astronomy so often. But what needs to be known here is that when the mass of the stellar core is bigger than 1.44 solar masses, the electron degeneracy pressure cannot support the remnant core, and it further collapses into even weirder stuff, which we will cover and which we have covered before. Hint, hint, go watch that video. Eventually, this hasn't happened yet, as far as we know, but eventually, the white dwarf radiates all of its heat and fades into black, making it a black dwarf in some 10 billion years. At this point, the star is extra dead, concluded some may say, making this the conclusion of this video. Or is it? No, yeah, it is. In later videos, we'll talk about the other paths of stellar evolution with more massive stars that create some very weird results. If you like this video, go ahead, like, subscribe, comment, please share. And if you have any questions, leave them in the comments. And as always, remember to keep wondering.